welcome everybody. Good afternoon to those in India. Good morning to those in the UK. Thank you for joining us for this joint Brunel IISc webinar. It's on the theme of sustainable manufacturing, and we're looking forward to hearing from Professor Monto Mani and Dr. Gera Troisi. So we will start off with Professor Monto Mani speaking on sustainability, fundamental challenges in buildings and design. The session is recorded. It's over to you, Professor Monto Mani.
Yeah, that's all right, I think. Many people. Yeah, thank you. Good afternoon in the UK and good morning, or rather good afternoon in India and good morning in the UK. Am I audible? Okay. So I am basically an architect working in the area of sustainability. I'm also with looking at sustainability science as in the interdisciplinary nature, the concept of sustainability itself. This is something that I've been doing since my doctoral work way back in about the year 2000. Then I've been looking at the translation of sustainability and examining sustainability in the context of the built environment and design. So I'm sharing my experiences here, and I'm carrying you through different aspects of my research. So we have a group called the Sudesi Group, Sustainability and Design. And Su in Sanskrit also means prosperity, and Desi also in one sense implies indigenous. On the English context, Sudesi, like I said, is sustainability and design, and we look at various aspects of the built environment, renewables, and we also looking at how design can empower people, support livelihood. So I'll just start with presenting the context of ecological footprint. And the idea is, does ecological footprint or a higher ecological footprint translate to a happy society or a society that is contented? And there are a lot of debates on it, and this is from a source from a book, Energy Development book, where there isn't a correlation between a very high ecological footprint and a high satisfaction with life. And this particular book, in fact, spoke of satisfaction with life from a non-econometric sense, as in it didn't look at what is your income, are you happy with the money or the lifestyle, but it primarily looked at, are you contented with the job that you're doing? Do you have time with your friends? Do you have time with your family? Do you get to do what you like to do? And those were the measures of satisfaction with life. And here you can actually see two paradigms. The one paradigm is sort of connected with the consumerist sort of economic premise that we carry today, where the more we consume, the more we are contributing to the economy, whereby we are promoting overall economic growth and things like that. Essentially, it means that go after your desires and you're happy. But desires don't necessarily have a upper bound, so there isn't a limit. So you are always on an ever-increasing trajectory. The second approach to look at this is have no desires and you're happy, right? And usually what happens is that up till our retirement, we follow the first part, that is we go after our desires. And post-retirement, we follow the second half, saying, okay, have no desires, I'm going to live a simple life, I'm going to contribute to society, I'm going to meet my friends. But what happens is that the damage that we would have done as individuals in the decisions and the lifestyles that we have lived, both on ourselves and on the society and the planet, doesn't get undone by what we decide to do post-retirement. And I think each one of us can reflect on this in our own personal capacities. I can dwell on this for hours, but just to pitch the context of where the crossroads of sustainability, in one sense, we are faced with. Then the fact has always been that an increasing income has necessarily not led to happiness, and this everybody is aware. we are on social media, but everyone on social media have issues with, you know, poor image and, lower self-confidence and things like that. So we are grappling with a lot more problems than probably what people faced a few decades back. Yes, there were issues of hunger, malnourishment, diseases, and things like that. But by and large, if you look at the projection, there is reason to stop and think. And I think the COVID, that lockdown gave us some time to actually pause and reflect on whether the course that we're taking is actually right. And climate change is also driving home the point in terms of, okay, there is something that we really need to examine here. And I'm going to start with the debate between zero energy and energy zero, right? Now everyone's talking of net zero and things like that. And there's a very fundamental difference in these two dwellings that you can see right now. The dwelling on the left is what we call zero energy, because they don't have access to electricity, which is the face of the modern world. And the one on the left is our lab in the institute, where I'm trying to generate as much electricity as I consume. So technically, I'm net zero, right? But both are not the same, not requiring energy at all in terms of electricity, and generating as much as you consume are both not the same. Right? And then we went into examining these houses, and this was a study we had initiated way back in 2004, right? And this was to study how do these dwellings actually fare climatically. And when we went into just examining the thermal performance, we had to even study their agricultural practices, because the crops that are the thatch roof that you see comes from the crops that they grow, and they specifically choose seeds which give them a particular height or length which they can use for the roof. So they use that every 5 years or every 7 years cycle, and so that the roof can be done up again, right? And these were the temperature profiles that we measured. That is, temperatures can go up to almost 41 degrees Celsius in summer. And the green line that you see is the temperatures on the indoor surfaces of the wall. And you will see that these are non-air conditioned houses, fantastically comfortable without the need for any energy, right? And there is a lot more to this. I will share in the following slides. And then when we look at end of life, all of these materials are derived from nature, technically within about 10 miles, or many of them actually from their own farms. They live very close to their farms. And you will find that end of life, the entire house becomes part of nature. There's no toxicity to deal with. There is nothing that you need to reprocess or salvage or store, or like the issues of microplastics or plastics that we're facing today. And as with any modern society, I think they are also going through transitions. And the first transition that you see is connected with the roof. They will go for a material that is more permanent, and then the walls change. And there is a dimension on the social front which reflects these transitions. I'm not going to discuss that part now, but essentially what it means is that when a member of the family earns a little more money or gets influenced by living in the city, he will come back and make changes to the dwelling, which will show that, okay, he's no longer poor or no longer backward or no longer uneducated, and wants to build a modern house. And then the community or the family gets fragmented. And that also reflects in the built environment, where he doesn't want to build a house close to where the parents lived. And I'm sure in the West, this whole fragmented nuclear families, it's far more evident. But the Asian cultures, I think the concept of a joint family to some extent is still valid, which is again reflected in the buildings, because you'll have a much larger house with multiple rooms with many families and relatives staying together. And then what happens is that with these transitions, we find that with just the footprint of the house remaining the same, a traditional house of earth moving towards a modern house using cement, there is almost 6 tons of carbon dioxide emissions per house. And we found that when we take a country, a populous country like India, you will find that this transitions can contribute significantly to uh, the carbon dioxide emissions. So we have published this study way back in 2012, and which means that if you take India and China put together, where 65% of the population is still rural, and which essentially I'm talking of about 1.8 billion people, and they want to adopt a modern lifestyle, where are the resources? So despite the fact that our per capita energy and resource footprints are among the lowest in the world, but the sheer population size actually is mind-boggling in terms of their aspirational requirements. And then what we also found is that in the built environment, there are two dimensions. One is the embodied energy, which is the energy going into manufacturing and commissioning the buildings and building materials. And the second aspect is the operational energy, which is, say, the air conditioned, the lighting that we use, and all of that to keep ourselves comfortable. And we find that for traditional dwellings, the embodied energy is less than 2 gigajoules per meter square, whereas the operational energy less than 1 gigajoules per household per year. On the other hand, if you look at ultra modern buildings, the operational energy goes from 1 to 42, right? So we almost have a 40-fold increase in our operational energy consumption when we move from traditional dwellings to conventional or modern dwellings, right? And then we are faced with the issue of, okay, where do we the source, where do we derive the energy from? And then we look at, say, building integrated, gasification, wind, nuclear, offshore wind, right? And that is just there's absolutely, in one sense, we our insatiable chase of energy is not going to stop for some time now, even if it is under the context of clean energy, which I will debate by the end of this presentation. And then we also look at adaptation, right? Today, with climate change coming in and buildings being on the forefront, because we spend almost 80-90% of the time indoors, and the fact that temperatures are rising across the world, whether climate is getting more erratic, unpredictable, and then where do we go, right? And this is where we actually did a study on that if the current climate is no longer holding good and the dwellings which are designed for that climate have to adapt or need changes, then how do we look at it? So we looked at a specific place like Sugenelli, which is very close to Bangalore, where my institute is. And we said that what if it got drier and what if it got a little, moved from warm humid to a temperate zone, a little cooler. And what we found is that we studied uh, two types of dwellings. We studied vernacular, which is earth-based, thick walls, thatch roof, typical dwellings. And then we also looked at conventional dwellings. And what we found is that the two graphs that you see and the shaded lines that you see is the thermal comfort indoors, right? And we will be plotting the the thermal comfort points for conventional dwellings and the vernacular dwellings. And we find that the temperatures within vernacular dwellings are very, very, uh, you know, comfortable throughout the year. And when the climate change were to influence, we find that if it were to get hot, dry, and if it were to get into cooler or temperate, the vernacular dwellings are far more resilient to withstand climate change than conventional dwellings. Conventional dwellings are either going to need more insulation or thermal mass or energy to provide and keep the indoors comfortable, right? So again, but the irony here is that the vernacular dwellings are changing, and they're all trying to go towards modern dwellings, and modern dwellings are not necessarily so resilient at withstanding climate change, right? In fact, we had published this in scientific reports, which is published by Nature, and it was in the news and all of that. So, so again, say this is across the world, And this other study that I told you, which got published in scientific reports, received a lot of attention because a large share of the world's building stock is still vernacular, even in the UK. In fact, we have a project with the University of Bath where we are examining how earthen dwellings fare as compared to other conventional dwellings. And we are examining indoor air quality and looking at respiratory comfort and many of those parameters connected with the building materials per se. So here again we looked at three different climate buildings in three different climatic zones in India, and you can see the picture. You can see are the transitions that are happening. That is moving. The ones on the left are traditional constructions, and ones on the right are modern constructions. Incidentally, in the West, what I'm saying is in Europe or in the US, the ones on the left are actually houses which the super rich will build using earth or stone or traditional, and the ones on the right are buildings which are very common, and are air conditioned as well. And here we found that the traditional dwellings, vernacular dwellings, are far more resilient to withstand climate change. When we looked at three different climate change scenarios as projected by the IPCC report. And this was the article that received a lot of attention globally in terms of how do we examine or revalidate vernacular dwellings across the globe. Then we come down to smart buildings, right? And this is again work which my doctoral student is just submitting. It connects with we using a lot of sensors to save energy. But the issue here is the sensors used for devices like, say, LED lights, right? Air conditioners, occupancy sensors. Very often, what happens is that the embodied energy associated with the sensors themselves are not accounted for in the overall energy computations. So what we did is that we coined this term called energy neutrality. And the energy neutrality essentially means that the sensor network that is put up to save energy recovers the energy saved based on the appliances that are connected to it. But there is also a catch here that today our appliances have gotten very, 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 very efficient. So the scope to save energy has actually gone down because appliances are very energy efficient by themselves, right? So the only scope there is either use it or not use it. There's no question of using the appliance in an efficient way because anyway it's efficient, right? So we coined this term called the gram per wattage ratio, which means that the grams of the sensory network and the wattage connected to it. And we actually compared, say, the old filament bulbs, which were very inefficient, where the scope for saving energy was much higher, and LED lights, which are anyway very efficient today. So the scope for saving energy is much less. And what we found is that the incandescent light, the energy payback period is almost a year. That is, recover the energy going into the sensory network. But for LED lamps, we find that the energy payback period when you use LEDs to connect them to occupancy sensors in almost 11 years, right? So what we're trying to do is that in a smart building, we're trying to examine where does it make sense to put sensors and where it doesn't, right? Even a hard switch is enough. And we're bringing in factor in the fact that factor in uh, the the material intensity associated with the sensors itself, where they are manufactured, where are they sourced from, looking at the transport energy, and then almost including the packaging material and the delivery and the installation of these sensors. And we found that the transport energy is very high. So if we were to locally manufacture and locally consume them, a significant amount of carbon footprints associated with our lifestyle can actually be brought down. Then we will go to manufacturing. Again, this is another student's doctoral work where we are looking at manufacturing of a product and the associated active impacts. And very often the embodied impacts are what we account for. And this we coin these terms active impacts and embodied impacts to distinguish between the energy or the emissions that happen during the use of the product and the energy and emissions and the material intensity that happens during the manufacture of the product. The energy going into the manufacture of the product, manufacturing a product is easy because it's within the confines of a factory, and any energy or material saved actually translates to an economic benefit. So the factories are actually happy to pursue them. But what happens if the product goes out and the usage of the product, energy going into, say, charging the device or operating the device, and the impacts associated with it on the user, right? And classic examples today are, say, the microplastics that are released from, or the microfibers released from synthetic clothes that go down the washing machine and go down into our waterways. The radiation exposure we are subject to from mobile phones or Wi-Fi points, they are really not accounted for very, precisely when we look at life impact studies or life cycle analysis. And that is where we are looking at, and we are trying to characterize manufacturing and products from the various geographies that are involved. So this is where we are looking at, like, material is extracted in certain places, then it's getting processed somewhere, then it gets refined somewhere, then it gets productized somewhere, and then it gets assembled somewhere else. So we're trying to associate the various geographies involved and see in those local geographies what are the impacts associated with that particular activity. So I'm going to skip this. So the idea here is that sustainability, again, we examine it, the overall process, the various stakeholders involved, the data analysis that happens. We collect the particular planetary or the local ecosystem services that are vulnerable in those geographies and try to bring that in, and then try to make an assessment. So there is some, this is again in published work, and there's some more clarity that we've given in terms of effectiveness and efficiency. The thing is that efficiency is I would say the wrong road that we've been pursuing, because the pursuit of energy efficiency has only resulted in the products becoming more affordable, cheaper, and eventually people own more of it. And a straightforward example is, if you examine, or everyone examines their own lifestyle, what we were consuming 10 years back and what each of us is consuming today, we are consuming way more today, despite the fact that the appliances we are using are way more efficient, right? At one time, it was just one computer or a desktop computer to a family. Today, it is not only one laptop to an individual, it's a mobile phone, it's a tablet, and we probably have a spare mobile phone, right? And if you start accounting for all of that, you will find that our energy footprint has only been increasing. And moving forward, our economies are not really talking of reducing the per capita energy consumption. Then the issue of the complexity with which we understand sustainability. So the safe lighting part, I will touch upon here, given the fact that LEDs are a part of our lives, and our eyes are exposed to LEDs, starting with the mobile phones, our televisions, our computer screens, and all of it. Now OLEDs have come in. We'll have to see how safe they are. But the issue actually surfaced in Europe, where a lot of teenagers were faced with the issue of blind spots and permanent retinal cell deaths, and they trace this to long-term exposure to LED, particularly mobile phones. Right? In India, in the tropical regions, we are sort of gifted, because whether we liked it or not, we are exposed to a lot of natural light, a lot of sunlight. So it doesn't impact us as much. But the problem is that LEDs today are super white, which comes with a very large spectrum on the blue side, which is the slide that you see with the marked oval. And this blue light is what causes problems. And all of us would be familiar today that monitors come with low blue light filter and things like that. And what we did is that, and this happened in the lab where we had moved from typical fluorescent based lights to LEDs, and the students started complaining of headache and eyesight related problems. And then we finally came up with a filter. Anyway, this is also accessible online, it's free for all. We came up with a filter. We identified a filter called Capton, which is actually a polyamide film, which very specifically cuts off this blue light. And in the interest of public, we actually made this finding accessible to people. It's out there as a publication, and a lot of industry has accommodated it. But I'm talking about work that happened about 4 or 5 years back. Today, I think the industry has moved forward with LEDs, which are much safer for the eyes. But I've received emails from many of them from Europe, Germany, UK, where they have written to me saying that they are having problems with the eye inflammation, and they came across our article and they were asking us what do we do. So what we've done here is just made this particular commercially available tape. This is a tape that is used extensively for 3D printing applications. And yes, the we have not examined the other aspect of how it impacts the other light spectra, like how it affects the red and the blues and all of that. But at least it cuts off the specific blue light in that spectrum, which actually is damaging to the eyes. Now I will come to when I said clean energy. And globally, in fact, even wind energy is considered clean, but there are debates on it because there are a lot of composites that gets used, what happens at end of life. And in fact, there is a paper in Nature published by a colleague of mine, Maria Tacker, and she's actually said that windmills displace the larger order birds, the raptors. And when the raptors are displaced, they have an impact on the reptilian population, right? And so it's not that anything that we call clean in one dimension is clean in every other dimension. Here again, photovoltaics, we are going to end up with an exhaustive amount of photovoltaic waste, which we don't know what to do with. And people are looking at recycling, material recovery, but they're primarily looking at the silicon and some of the precious metals that go in. The rest of it still goes to the landfill, and anything that goes to the landfill actually impacts water. So what we did is that we actually examined whether photovoltaics can be used as a building material. Yes, in terms of building integrated photovoltaics is being used, but we are specifically looking at degraded photovoltaics. And again, there's a PhD thesis examining the various transmittance, solar spectral transmittance, as well as the thermal transmittance. We've subject the panels to a lot of experimental investigation to see how they would fare for various climatic zones. And this is again a work that we will publish shortly. So that is a small, end of life photovoltaic lab that we have. Again, this article has been out and a lot of, publicity that we've received for this. Then the last part I will cover is sanitation, and I will just take another 2 or 3 minutes. That's it. So this was the work that we took up in 2004, 2004 and 5, when there was a tsunami, which everybody is aware of, and how it destroyed the coastal communities completely. So we were asked to provide housing and sanitation to a coastal community, and we were faced with a challenge here because this community had good drinking water within a meter and a half in the ground, right? And they were relying on it for hundreds of years. And what we had done was that we came up with the idea of not contaminating the groundwater. We looked at recirculating the nutrients coming out from our excrements close to the surface of the soil, where the community can have a kitchen garden, and also the fact that we raised the entire toilet and we had something called a post filtration chamber, which actually regulates the level of the water or the sewage within the septic tank. So much so that this is probably the only sanitation unit in the world which can resume functioning even if it is flooded completely. Right? We actually received recognition from the Swiss Environment Foundation way back on technologies or designs that protect groundwater. So we built about 160 of this for an entire village. And this was way back in 2006 that we handed over this housing and sanitation units to the community. And when I visited this place again in 2017-18, nearly 60 to 70% of them are still in operation, still functional, which is actually very good. And then we are looking at rammed earth for construction of affordable sanitation units. And I'll come to the last part. This was something that we did about 3 years back, where we got the Lexus Design Award for India. This was also showcased in the Milan Design Week 2019-20. As in, it was the last Milan Design, I think, that Lexus had done, after which the COVID broke up. So we came up with a small sewage or a sewer line cleaning system and inspection system, which is completely operated on the mobile. And this is something that we made from a water bottle, actually a steel water bottle, which we actually put in some sensors and cameras, and so that somebody could inspect what is there within a sewer line to see how deep is the clog, and mainly to prevent people getting in. And we also had a pH sensor, a temperature sensor to say whether the water is safe, is it acidic. And this was the cleaner rad that we called it, that we made to be it was completely automatic, controlled on the mobile phone. You could actually see what this device is seeing on the mobile phone. And we also even came up with a small probe to understand the nature of the clog, whether it's hard, whether it's fibrous, whether it's debris, based on which we can actually change the head of the instrument required to declog it. And yeah, so I think with this, there are some questions that I have as to, very often we talk of efficiency, that is minimum pollution or low energy or low impact. But these are actually misleading, because if every vehicle were to emit very little of whatever emissions they are, and you increase their consumption for all the aspirational people who want to buy it, the net impact is going to be very high. And that's what we are facing today, right? Everyone wants the economy to boom. At the same time, they want the environment also to be sustainable and support the lifestyles that we have. So it's a tough call. So I think we need to have a paradigm shift from efficiency to effectiveness. And one fundamental change we need to do is, can design help in reducing the per capita energy and resource footprint that we carry right now? And I think that is the transformative role design has to play. If sustainability is something, it has to support. And I will stop with this. Thank you.
Okay, thank you very much. We'll move on to questions and answers at the end. Now, very delighted to introduce our second speaker, and that is Dr. Gera Troisi, Brunel University London, and her talk is on LCA as a tool for sustainable manufacturing. So it's over to you, Dr. Troisi.
So I just share my screen with you, yes?
Yes, that's right.
Okay.
We're seeing it twice.
Now you should be able to see it once.
Perfect.
Right, is that okay? Lovely.
Yeah, perfect.
Okay, so hello everyone, good afternoon in India, and that was an excellent, really interesting. I agree with so many of these dilemmas. I mean, I agree, I perceive them and I see them as well in sustainable development, that we're kind of like robbing Peter to pay Paul, and everyone's saying everything's green and net zero, and we really need to scratch deeper and think bigger. So what I've tried to do today is, I'm not giving you an overview of my research, I'm just focusing on a couple of something that I've learned that I want to share, because I think it's urgent, which is that a lot of projects, especially EU funded projects and projects I see funded in the UK, involve life cycle assessment for sustainability. They put life cycle assessment in and think, oh, right, we're looking at sustainability. And it's not the same thing. So I'm going to explain why and show you why we use LCA, what it is, and how we use it, and what the shortcomings are, and when you're actually trying to develop a sustainable product or via sustainable manufacturing methods. So there's smoke and mirrors going on here. So I'm kind of trying to expose what's going on and get you all thinking when you are in the stage of designing new products, manufacturing, use and end of life, to think about all of these concepts, because it's quite revolutionary in terms of solving sustainability problems for real, by thinking outside of just the LCA box. LCA is just part of the package of trying to make a sustainable development. So without further ado, I'm focusing on some aerospace dilemmas that I've been working on with some of my Brunel PhD students and other project students as my example case studies to sort of try and ram this home. Okay. What are the drivers for sustainable products? In the UK and Europe, very much we're focused by regulation. The bane of an industry's life is compliance. And I suppose in India, you're not so under so much pressure, but when we do research in Brunel, especially, everything has to be industry facing. A lot of our sponsors are are from industry or are collaborators in our research. So we have to have an industry facing outlook and compliance consideration. We use things like international standards, like national standards and international standards for the design of sustainable products. We think about sustainable procurement for the extraction and production of materials that we need for manufacturing. When we come to the manufacturing stage, we think we've got things like the chemical regulations on our like REACH to comply with. In the workplace, we've got COSH, control of hazardous substances and restriction of hazardous substances enforced by the Health and Safety Executive. Then we've got the environmental permitting regulations under the IED directive for any emissions to the air, soil or water that can impact on the environment. Plus, you've got any considerations for impact on workers, and we should be worried about them. Workplace exposure and personal exposure to contaminants or other toxic materials in the workplace. We have to worry about that. And there's the OSAS management system that looks after that, and various health and safety regulations which enforce the WELL and PEL limits. And then at end of life, we've got things like the end of life of vehicles. If we're talking about cars and aircraft and other vehicles, we've got the waste electrical equipment directive as well. We've got to think about lots of things which all should be taken into consideration when we're designing a product, manufacturing a product, using an end of life. Furthermore, for true sustainable engineering, we need to make sure we look at the whole life cycle, which brings me to my next slide, just in case people haven't got any LCA knowledge. I don't know how much experience you'll have, but life cycle assessment will basically look at environmental impacts over the whole life cycle, cradle to grave, from extraction, manufacture, use and end of life, and the transport and packaging in between. Over each of these stages, we look at inputs, that's material and energy, and outputs, which is emissions to air, soil and water at every life cycle stage. And why we're doing this is the life cycle will help us break the cake down into 4 nice slices, or 5 if you want to add transport as a 5th stage, so that we can bite each piece off and actually look and see where are our problems for the environment. And life cycle assessment looks at environmental impacts, not sustainability impacts. Very important point to make. But it does help us visualize, contextualize our problem and be able to look at it in a more digestible fashion in this way, to see where exactly our environmental impacts are so that we can troubleshoot and mitigate. So what we do with the LCA, we first of all have to decide what it's for. And this is really important because it dictates the outcome and the results of the LCA. Why are we doing it? Are we doing it for marketing, competition with other products in the market? Are we doing it for ISO 14001 accreditation and environmental product labels? Like all of these big companies will, but only the very big companies actually bother to make environmental product labels for their products, where they have a look at the environmental impacts. For example, here for concrete, they're looking at all of these different environmental impacts over the life cycle of their product. Aircraft and cars, it all depends on the manufacturers to how much corporate social responsibility attention they pay to their products and how much communication and transparency they want to the market, to the consumers. Other times it's for compliance, other times it's for product profitability, which is a sensible thing. If you want to make your product more profitable, making it more sustainable actually does make it more profitable in the long run. And there's a lot of value judgments going on when who is commissioning the LCA. So you've always got to look at, when you read other people's results from an LCA, ask these questions of the LCA, because you can't interpret the results without knowing what the objective was, because they can be skewed. What are the steps in life cycle assessment? So to be credible and publishable, we have to use the ISO 14040 guidance, which comes under the envelope or the umbrella of ISO 14001 Environmental Management Standard, which is goal and scope definition, inventory analysis and impact assessment, with interpretation at each stage. Naturally, in the goal and scope, we're setting the boundaries, defining our functional unit and putting in the boundaries around what we're going to study. Okay, are we going to look at all of the life cycle or just part of it? The inventory analysis is basically our shopping list, bill of materials and other information are consolidated and entered into an inventory for every stage of the life cycle. And then we use software, thankfully, to help us with this. And then we have an impact assessment where we translate those chemicals and materials going in and stuff coming out to translate that into actual impact on the environment, whether that's be climate change, eutrophication, ozone depletion, acidification, ecotoxicity and human toxicity, etc. So specific environmental impacts. Life cycle assessment will give us multiple environmental impact category results at the end, not just one environmental score, which unfortunately what is disseminated more publicly. It's actually gives you specific environmental impacts that are happening as a result of your product's use or disposal at different life cycle stages. So you can really understand where your problems are if you want to improve your product. A very important thing, again, is the functional unit. We basically have to define our product that we're looking at as its function. So if we're using a light bulb, how much light we're going to get out of it for how long, so that we can then compare it with other light bulbs and make a decision as to which light bulb to go with. Or if you've got an existing bulb and you're a manufacturer and you want to change it, you want to make it reduce the environmental impacts, you need to define a functional unit so you can compare it with other designs, or previous designs, or your next design, and so on. Otherwise, you need a level footing so you can compare products on a one-to-one basis. So boundary, not only are the functional unit an area where there can be errors made, because a lot of people see things in different ways, how they define function, and therein starts a failure, if you like, in the whole analysis, which will reflect in the results at the end. So when you look at results, go back to the functional unit, make sure that has been defined properly before you believe the output of the LCA. Similarly, border police checks, these are really important. Again, people will publish life cycle assessments and say, look at my net zero product, but they haven't looked at all of the life cycle or only part of it, or they've removed or eliminated or assumed or excluded certain elements of the life cycle. And by making those choices right at the beginning of the life cycle assessment, the whole rest of it could be wrong, depending on what you're trying to look at or what they've said the purpose of their life cycle assessment is. Very often they'll say, we're doing a life cycle assessment to show the sustainability of our product has improved. And those are big claims. And when you actually scratch the surface and look deep into the methodology that's been used, so the functional unit definition, the boundaries, the assumptions and limitations in the goal and scope phase of the life cycle assessment, you'll find the truth lies there. And who is the commissioner? Is it the manufacturer, or is it an academic? All of these kinds of considerations need to be looked at if you want to understand the truth behind the results of a life cycle assessment. From an academic standpoint, when I say the truth, okay? So yeah, and there's nothing wrong with picking cradle to gate, for example, because you may only want to be focusing on these stages of the life cycle because you have no control over use or end of life, perhaps. So it might be best available technology, not entailing excessive cost, or BATNIC, to just look at these stages of the life cycle and be more cost efficient and time efficient. It really depends on the commissioning of the life cycle assessment, why you're doing it. So again, always go back when you're looking at products, your product, how to improve it, and you're looking at other publications or reports on LCA, you have to scrutinize all of the scope and boundary to really try and make some comparisons with what you're doing and how you're going to improve going forward. Here, for example, we've got an example of a life cycle assessment for bandages. They've left out the application and use because that's very much determined on which country, which community are using these bandages. So they haven't modelled that in their life cycle assessment. So that's something to take into consideration. But they've said you can actually leave out something in the middle of the life cycle, but you have to differentiate and define at the scope and boundary definitions at the start of the life cycle assessment. So when you've done your life cycle assessment and you've got your results, you've started to find which stage of the life cycle has got the problems. You must also make sure before you make proposals that your product is now better for the environment, that you've looked upstream and downstream of the life cycle stages, because what happens, and I've seen this in publications and recent publications and big decisions in aircraft manufacturing, that they look at a pinpoint tunnel vision of one stage of the life cycle and don't properly examine upstream and downstream to make sure there's net environmental improvement. And I'm just talking about environmental improvement because this is life cycle assessment, not a life cycle sustainability assessment. So all stages of the life cycle have to be considered, all inputs, all outputs, to really make sure at each life cycle stage that once you've made a change, a mitigation, an improvement, that you haven't just passed the buck somewhere else, like robbing Peter to pay Paul, as we say in England. So our mitigations, we have to make sure that everything we put in place is actually for net environmental benefit. I've just put BATNIC in as a concept because it's enshrined in the IPPC regulations, and you can use that as a manufacturer to justify sometimes, I think, because we're very much feeling like, oh, you know, we have to spend a lot of money in improving the products, you know, offsetting environmental impacts and so on. But there is this argument that our technology, what we put in place, has to be BATNIC. So regulatory bodies understand that we have to still be profitable, that we have to not, you know, close down the business or make the product no longer viable because we're trying to make it green. BATNIC allows us to try and use the best available technology that's the best in the current market, the best current practice or state of the art. That's fine to use as long as it's effective, and you don't have to go beyond that and use excessive cost. So that's justifiable. So if you haven't used the absolute latest, most expensive technology, it's not the end of the world. As long as you've used the current use of technology to try and mitigate emissions or reduce energy use and material use, that's what's acceptable. That's fine under the regulations. And you will get people like the Environment Agency coming to check your environmental mitigations in your industrial process or manufacturing, and they will see that you've used BATNIC as a way to justify that you've tried your best to make sure you've reduced emissions, you've got your environmental mediation is there, and it's all the best available technology, not entailing excessive cost. They don't expect you to go out of business. They expect you just to show good practice. And I think that's a bit of a save and a sigh of relief for a lot of manufacturers who are trying to make their products more green, but at the same time still make their profit, otherwise they wouldn't exist. I won't have time to go through that. I will go through this, which is more important, because we're running out of time. We're running late on the session. So warning, when you do a life cycle assessment, make sure you look at the objectives, the functional unit, boundary and assumptions. It's not an exact science. Life cycle assessment has to have, when you get your results, some really big differences between a product to be actually believable. The error sources, the amount of error can be 50%, even 70% between. So that's how unrealistic it can be. It's a very generic model. It's very standardized models and databases that you're using, which normalize everything, which is not what nature is about. We have these databases in the software, which I'll talk about in a moment, which will be something that we call upon in our life cycle assessment. And we have to pick the data as according to what information we've got, because very often we don't have the information in life cycle assessment. So at the end of the day, data gaps will be your biggest problem when you do a life cycle assessment. And when you've used standardized data, arbitrary data, median and mean data that are in a database, you've already increased the uncertainty and error in the results of your life cycle assessment. So within the life cycle assessment community, when they see results of 2 products with about 10% difference in their environmental impact, they're like, it's not a really big difference here. We can't really make a decision about which product is more sustainable, more better for the environment, because a 10% difference isn't something to write home about and have a party about. You need to make bigger improvements, like 50, 60, 70% improvements, to be beyond the error that is in the inherent error from the life cycle assessment methodology. And I think that's something that a lot of people don't know. This software, the 2 software packages that are used in industry are CIMAPRO, which is from Prairie Consultants, and Gabby from Sphera. And I just want to give you some insights, because I've used both, and about cost and user friendliness and so on. So CIMAPRO is more, it's not very user friendly. It's a bit old school. It's older than Gabby. So they haven't got the funding, to be honest, with developing a really swish interface, because they're not for profit, interestingly, which is why I support them as well, because I think that's what we should be doing if we have a sustainable development outlook. Whereas Gabby Sphera are much more profit orientated, they're much more expensive. Every bit of help you want to ask from them is an extra cost. And so that you don't get a lot of support as much as you would from Prairie Consultants with CIMAPRO software. Also, CIMAPRO software incorporates the EcoInvent inventory, which is the most comprehensive inventory database. So the bills of materials, most materials you'll find in EcoInvent, whereas with Sphera, you'll have to buy on extra databases for this, for composites, for biopolymers, and everything's add-on. They have a basic environmental footprint inventory, but it's very limited. So you have to pay extra on top of an already expensive product. It is more user-friendly because it's newer and they've got a better software engineering team. So they've made it more colourful, intuitive and user-friendly. So you get clearer results. But if you want to plot by life cycle stage, extraction, manufacture, use, disposal, it's clearer. And it's not so clear, unfortunately, with the SimmerPro software. It's a bit more, you know, you get really small legends. It's not very pretty. So what I end up having to do is export the data to Excel and then make it look nice. But it's much more easy to work with SimmerPro, because if you have any problems, you just contact them and they give you lots of support, and it's very cost effective. Question why I'm using these two softwares: because I work with industry. If you want to be taken seriously by industry, or your publications need to be taken seriously by an editor in a high impact journal, you need to be using these two software packages. Everything else is kind of like not viewed with the same vein. So this is the best practice for software for life cycle assessment. So if I were you and you have a limited budget, especially if you're in education in the institute there in India, the Institute of Science, I would go with SimmerPro because they're very supportive of educational institutes. Conflicts with what I've seen with Gabby. So yeah, we've got both softwares, but we use this for class and we dip into Gabby for some other bits and pieces sometimes. So that's enough about LCA insights. I just want to show you in reality what I mean. So we were looking at sustainable materials and aircraft manufacture in the UK. We've got the Airbus the Airbus series, and there's a lot of media coverage that we've got green aircraft. A lot of airliners are promoting themselves to the public as, you know, the most sustainable airline in Europe. And where do they get these claims from, and what have they done to justify this? And I scratched the surface and went back to have a look at these, because we do a lot of materials research. So I just wanted to match the research with what the talk is in terms of environmental speak. So the Brunel, we've done quite a lot of studies on LCA to look at these materials. A380, for example, we did a cradle to grave for life cycle assessment, and capture an end of life, and the end of life scenario was just landfill, so it just goes to landfill. They didn't incorporate the interiors, and they used a completely different functional unit. The functional that unit they used was the tons of material per kilometre, and that's fine. So it's different from our results, but so you could argue that's why they're getting different results. But I'm doing another life cycle assessment, which is using their functional units so that I can then compare and contrast with them. But the really interesting thing was that they used a service life of 25 years and 150 million kilometres. R1 was 25 years. And even that is exaggerating what really happens in practice, because aircraft retire around, on average, 24 years of service. They don't get continued as passenger aircraft because the failure rate increases with time due to the fatigue of the aircraft, or the taking off and landing just really puts a lot of stress on the aircraft. So in developed countries where you've got the airworthiness requirements, they say, look, no, this has got to be decommissioned. It doesn't meet the airworthiness standards in our countries. So you're going to have to decommission that aircraft for passenger use. But then what does the owner do? I'm not going to chuck my millions in the bin. I'm going to sell this to a country which doesn't enforce their safety regulations of airworthiness in the same way, where it's a bit easier to use aircraft for passengers where they're not so safe. Or we can make them as cargo and freight aircraft. Now, the air miles will reduce significantly because there's less travel. It's a luxury thing in developed world. There's a lot of air miles. And as soon as those air miles have been used up in terms of airworthiness, those aircraft are decommissioned. So they don't last for 30 years. And they certainly don't end up doing 150 million kilometres of passenger miles. It might be cargo or a half empty aircraft, or very fewer flights. And the aircraft is suffering from fatigue from takeoff and landing more than just flying in the air. So these are really important considerations when you think about the life of the material as a ton of carbon fibre or a ton of aluminium over the whole life cycle of the true life cycle of the product. So what they did was they said that carbon fibre, yes, it causes more environmental impacts if you look at just the manufacturing of the extraction and manufacturing stages and the end of life of the aircraft if you use carbon fibre. So they found similar results to ourselves. And then they remodeled the same scenarios, these 3 scenarios. So this is carbon fiber. The 2 scenarios for aluminium, one is where they've assumed a 1-to-1 ratio of aluminium. So every ton of aluminium is that ton put into the manufacture of the aircraft. Then they also assumed that you'd have to buy 8 tons or 8 kilos or whatever your material unit wants to be. They took 8 lots, but only used 1 lot in the manufacturing of the aircraft, claiming, and this may be well true, but I'm still waiting to hear back from manufacturers, that there's so much wastage in the manufacturing process of the fuselage and certain other parts that you lose that much aluminium. And they wanted to try and take that worst case scenario and the best case scenario and model it against carbon fiber when they took the use phase into consideration. So all of these 30 years of use, 150 million kilometers of flights, they wanted to see if with all of the benefit from fuel saving and offsetting CO2 emissions, if now the benefits for the environment are there. And they showed that there were. So with the 2 scenarios for aluminium, they've got higher millipoints, which is the environmental impact, than carbon fiber full life cycle. Okay, which is very conflicting with what others have said. It all depends on how you define your functional unit, how you define the lifestyle or the life use of an aircraft. The devil is in the detail. So before you make any decisions as a manufacturer, you should be looking at all of this. If you're Boeing or Airbus or Bombardier or whoever you are, they should be really teasing out the details to make better decisions at the design stage before making an aircraft, because design stage is where you make the best benefits for the environment, not retrospectively at the use phase, because you're responding to carbon emission taxes suddenly being imposed on aircraft, which was really new. I think it was in 2018, around there. Suddenly aircraft air miles were incorporated into the carbon trading system. So airlines have to make sure that their emissions are within limits, and they get charged for exceeding their CO2 caps. And so there's taxes there that they're paying, plus fuel charges have gone up because of as we know, from inflation and so on. So there's very much, I think, the market forces and regulatory forces pushing aircraft manufacturers to only focus and look at the life cycle stage of use phase. So what are the sustainable manufacturing decisions, the sustainable definitions we should be making, not just looking at environmental impacts, looking at the whole picture. So yes, the carbon fiber saves fuel and helps airlines meet their targets, emission caps, and avoid penalties. And there may well be lower overall impact over the life cycle stage, but findings are conflicting. And what we also need to remember is the End of Life of Vehicles Directive, which is applicable to the UK, European Union, the States, the United States, and I believe Japan as well, where they have enforcing targets year on year. They're looking for manufacturers to make their products recyclable. The automotive industry is getting there. They're doing really well, but aircraft are seriously behind. I think the best they got to was 86% recyclability with a Boeing. I can't remember which one it was, but it was mainly metals. There was virtually no carbon fiber in it. So if you put a carbon fiber aircraft into this question, you're going to say, no, we're not meeting compliance for end of life of vehicles. So that's not sustainable. Sustainability requires compliance with regulations as one of its requirements. And so does ISO 14001 accreditation and so on. So recycling CFRP, that's something that the aircraft manufacturers are pushing towards, pyrolysis. But it is expensive and costly for pyrolysis to recycle the carbon fibers, and then they generate carbon fibers which don't have the same mechanical properties as the new fibers. They're actually inferior to the new fibers when they're manufactured in terms of mechanical strength. So that means there's a limited market and they can't be reintroduced back into the aircraft, which is so why recycle them at all if you're going to have to pay a lot of money and energy to recycle these fibers at the end of the day. So I'm aware we're running out of time, so I just want to quickly talk about another sustainability issue for aerospace manufacturers. This is more for the landing gear of aircraft. So you've got high strength steel struts in the landing gear, which really suffer on takeoff and landing. So you have high fatigue. It's a fatigue critical surface, and airworthiness requires that they can last for 10 years. at least in service. So chrome is used, hard chrome is used to plate these cylinders that go in and out during the landing process and taking off. And chrome uses highly toxic chemicals, class 1 carcinogen, respiratory toxicants, and so on in the plating process. And these were banned in 2018 by the REACH regulations. So it's not sustainable to use these chemicals anymore. Indeed, most heavy metals, cad, chrome, nickel, they're all being banned or on sunset. Their sunset dates have been approached or are approaching or have been passed. And the REACH regulations are enforcing this, but they're getting special authorization, claiming that there are no other certified materials to replace chrome, nickel, and so on for the plating at this highly critical surface, which if this strut fails, hundreds of people could die. So it's a risk-based decision whereby they're trying to consolidate risk assessment, risk management with environmental management. And we're getting two different stakeholders at loggerheads. So there's no solution here because the stakeholders are not talking to each other and effectively to come up with a sustainable solution to replace these toxic chemicals. And people in the workplace are extremely exposed, and very often they exceed the workplace exposure limits set by the Health and Safety Executive. When they come out into the waste stream because of defective mitigation, which happens regularly, there are exceedances of environmental levels. So there's ecotoxicity, contamination of the local waterways, air quality issues. And the truth of the matter is, looking at the materials, there are drop-in replacements which match the mechanical properties of chrome. And they're very promising, but they haven't really been facing, there's still a lot of issues with certification, and that's the bottleneck to changing practice. Certification is and safety seems to stop us from being more sustainable because they're in a different sphere of engineering and mentality. They're only now starting to understand the importance of sustainability. Engineers, we're kind of thinking now it's part of our job description, but in the management of safety and for aircraft, they're still quite behind in this area, and we need to get everyone talking together. So we've done a study where we compared the environmental impacts of chrome, trivalent chrome, which is what the aircraft industry says is the best replacement for hexavalent chrome, and cobalt phosphorus, which is another really good material to work with. And we can see huge differences, big significant differences in life cycle assessment, which means there's something here over the whole life cycle, normalized to coating 1 meter squared of high strength steel to 127 micron thickness, which is the design thickness for the landing gear to refurbish it or to coat it for first use. And we can see in every single environmental impact that hexavalent chrome and trivalent chrome are poor performers, and cobalt phosphorus is hardly seen on the radar in comparison. And this has been around for over 10 years as a material and been researched and demonstrated by multiple stakeholders that this is a good replacement for hard chrome. But there seems to be some socio-economic political issues holding this back from being implemented. Also, cobalt phosphorus plates 8 times faster, well, 4 to 8 times faster, saving electricity and time. It's a drop-in replacement. It's much less toxic, as I've just said. Life cycle costing, though, is needed to demonstrate this, and we've done this on the right for environmental costs. So you can see the environmental costs offset by cobalt phosphorus are hugely more cost effective. You've got big environmental costs from hexavalent chrome and trivalent chrome, but to do a cost benefit analysis in terms of the cost of the material, the energy, and so on for the manufacturers or the MROs, you need to do a life cycle costing, which a life cycle assessment does not do. That's a separate assessment. You can also do things like capex and opex assessments. Also, we're saving on resources in terms of productivity, labour, occupational exposure, and emissions monitoring. All of that is saved, offset costs for socioeconomic benefits from going to this more efficient material that's also less toxic, less hazardous waste disposal, less sick days of the staff, so you've got less downtime in productivity. But that's not captured by a life cycle assessment. This is a life cycle sustainability assessment that you need to do. And unfortunately, they're rare and rarely done, and there's no internationally recognized socioeconomic life cycle assessment methods and tools and softwares available for industry. So those two software packages I told you about do not do life cycle sustainability assessment. They just do life cycle assessment, just the environmental impacts. That is changing because I speak to them, and I've found a tool that I use for for academic purposes, but there isn't one in industry that's available. So, of course, there's the negative always of change management, the cost and time associated with change management, and the airworthiness certification is still the stumbling block for any of these new materials. And basically, there's a lot of stakeholder conflict that needs to be resolved between the European Chemicals Agency, the CAA, the Civil Aviation Authority, and the aircraft manufacturers, and the MROs, the maintenance and refurbishment organizations, and the airliners that actually use the aircraft. So to wrap up, in summary, if I was you, if I was someone trying to make sustainable products, look from the design stage and also apply an integrated approach, an integrated management approach. You can't just look at environmental impacts. You need to look at quality and reliability of your device. So look at ISO 9001 and do things like fatigue analysis, mean time between failures, all of these reliability testing to make sure your product is made for longevity, not for obsolescence, which unfortunately the main driver for design tends to be how quick can we make something that fails so that people have to buy more and more and they just go to the dump. So we need to design something that's going to last for a long time, so all the embodied energy and carbon is made maximum use out of. We need to also think of the environmental risks, as I've just mentioned, also the occupational health and safety risks, and also the socio-economic risks in an integrated manner to actually design, manufacture, use, and think of the end of life of sustainable products. That's the true sustainability approach that I recommend from all of our research, and the way that we are doing our research and propose to others to do their design of their products, thinking forward in this manner. And also, if you're retrofitting or you have a product already, how we can change the product, thinking of this integrated management approach to get a better output for sustainable development to actually achieve sustainable development. And that's enough talking from me. I've gone over by a couple of minutes. I'm sorry. Thank you.
Thank you so much, Dr. Gera Troisi, and thank you so much, Professor Monto Mani.